Okay, let's take a look at using proof by induction, but with the application of proving a result for matrices. Okay, so what we're aiming to prove is that this matrix here, if you wanted to raise it to any power, you could just simply use this result here. Okay, so before we actually get into the proof, let's just think about this because it's the first time we've seen it. Like, if I asked you to work out 3 minus 4, 1 minus 1, if I asked you to work out that matrix to the power 10, you don't need to multiply the matrix by itself 10 times because obviously that would take ages. Instead, we can just say, well, if I wanted that matrix to the power 10, this result here would just give me the answer. So we're not adding stuff up. Obviously, it's not a serious question. It's a proof that there's a result that will always tell me what the power of this matrix is. And that if I wanted that matrix to the power 10, that would be, if I sub 10 in there, 21 minus 40, 10, and minus 19. If you want to check on your calculator, if you've got your graphical calculator, you can type the matrix in and raise it to the power, and it will give you that answer there. Okay, but that's like just what the result tells us. We're actually, obviously we need to prove that this result will work. Okay, so we're working with z, which is the integers, but z plus, so it's going to work for the positive integers. Okay, so we'll start with the first positive integer is 1. So let n equal 1. Okay, so we know that the result works for the first term. Let's assume true. Let's just assume it works. Okay, so now we're going to prove that the result works for the next term in the sequence. Again, thinking about, it's nice to know what you're aiming for. So if this result does work for the next term, it should end up looking like this, but I think maybe it's easier if we actually, because I don't think it'll look like that straight away. Think about what this will actually end up looking like, and then we'll know if we've got it. So k plus 1, 1 minus 2 lots of this, so minus 2, so that'll be minus 2k, minus 1, minus 4k, minus 4, 1 minus 2k minus 2, so that'll be minus 2k, minus 1. What have I done wrong there? Ah, right, sorry, that should be plus. Shouldn't it? That should be plus there. So that changes. I'm glad I spotted that mistake. So that would be plus 2k, so that would be 2k. Plus 3. Okay. So this is the result that we're aiming to end up with, and if we can get to this, we've basically done our proof by induction. Okay. Now the way that this works, if you think about it, right, whenever you're doing an induction, you assume this result works, and you need to figure out some way of using this result for the next term. So what would our matrix to the power k plus 1 look like? It's just indices, just think about it in next form. Like that would be equivalent to the matrix to the power 1 multiplied by the matrix to the power k. And by writing it like this, we're able to use this result to help us to prove that the result works. Remember, because that's how induction works, isn't it? Assume the result works, use this assumption to get to the next result as well. And that essentially we've proved that it will always work there. So let's see. We've got 3 minus 4, 1 minus 1. The matrix to the power k, we know is 1 plus 2k minus 4k, k, 1 minus 2k. Okay, so now we've just got to multiply these two matrices together and hopefully we'll end up with this result. Remember, when you multiply matrices, multiply rows by columns. So 3 times this minus 4 times this. First row, second column, minus 12k. Be careful with your negatives. Minus 4 plus 8k. Second row, first column, 1 plus 2k minus k. And then second row, second column. Let's tidy this up and see what we've got. Okay, so we've got 3 plus 2k minus 4 minus 4k, 1 plus k, and minus 1 minus 2k, which is exactly what we wanted, isn't it? Because just to justify that we've got this answer, if we write it in terms of k plus 1, so that would be 1 plus 2k plus 1 minus 4 lots of k plus 1, k plus 1, and 1 minus 2 k plus 1. Okay, and then write the same sentence that we wrote in the previous videos. I'm not going to write it out again. Okay. Okay, let's try one more. So we've got this matrix, which is a general matrix, 1A, 0, 2. So actually we're proving a result not for like a specific matrix. This A could be any value that we want. Like we could let A equal 5 minus 7, anything you want. And we're going to prove that if we wanted to raise this matrix, if we wanted to raise this matrix to the power of n, this would be the way that we could quickly do that using this result here. Okay, so let's follow the induction process, see what happens. Starting with 1, so m to the 1 would equal 1, a, 0, 2, m to the 1 would equal 1, 2 to the 1 minus 1, a, 0, 2 to the 1, which would give us 1, a, 0, 2. So therefore, because this equals this, we know it works for the first term. Let's assume it's true, and then use this assumption. So if we let, sorry, we should say assume true for n equals k. If we let n equal k plus 1, I'm going to skip writing the aim down, but I mean I would recommend doing it. We'll see at the end, but we can compare it with the results. If n equals k plus 1, m to the k plus 1 would equal m times n to the k which would equal 1a 0 2. M to the k is 1, 2 to the k minus 1, a 0 2 to the k. Okay, maybe pause and try and expand it out and see if you can get to that result. Let's see what we get. So multiply rows by columns. 1, a times 0, row by column, so 1 times this would be 2 to the k minus 1, a, and then a times this. Rows by columns, so 0 times 1, 2 times 0. Rows by columns, 0 times this, 2 times this. Okay, so we've essentially, if we get, you notice I didn't write the result down, but that's because it was probably easy to spot that we want to get, if it's going to work for k plus 1, that would just be 2 to the k plus 1, and that would be 2 to the k plus 1. So we can get to this. I've got my 1, got my 0, 2 to the 1 times 2 to the k is 2 to the k plus 1. Now look at what we can do here. We could expand this out, but again, I'm looking at the results. Common factor of a. If we take the common factor of a out of both, we've got 2 to the k minus 1 plus 2 to the k. 2 to the k plus 2 to the k is 2 lots of 2 to the k. Think about it, if you've got 2 to the k plus 2 to the k, you've got 2 lots of 2 to the k, and then we just use index form. 2 times 2 to the k, add the powers. And we've got our result that we were aiming for. Finish it off by writing a little sentence. And that's it. They're not, I mean, they can get a bit messy with the index form, but I think in terms of just realising the induction step for this, just write it as m times m to the k, use your assumption, expand it out, be careful with your algebra. You should relatively straightforward to get the answer for these ones. Alright, thanks guys.